Hi, let's take a look at how we can look at and find the natural frequency for a class of simple harmonic oscillators known as pendula. Now, the simplest way we could make a pendulum is have a particle at the end of a very long string, where that particle is just free to swing back and forth. We could make a pendulum out of any object by taking it, suspending it from some point that isn't the center of mass, and then displacing it so that the center of mass isn't directly underneath our center of rotation. So you notice me looking towards the ground. It's because I want to grab this meter stick right here. So an example of what we would call a physical pendulum would be if I suspend this from, say, this point in my right hand and let it go, it oscillates back and forth because gravity pulling from the center of mass creates a restoring torque, and that restoring torque is what is responsible for the oscillation. So if we take a look at just a basic extended free body diagram, if this point represents our center of rotation and this circle with an X in it represents our center of gravity or center of mass, that's where the force of gravity is acting straight down, and I'll call the distance between the center of rotation and the center of mass h. And I'm going to measure how far I've displaced that line away from the original vertical as an angle theta. So the torque that I get from the weight of that object is going to have a lever arm that's equal to this distance h times the sine of the angle that I've displaced it away from equilibrium. And the torque that I would have acting on my object is going to be equal to the weight of the object, the mass times gravity, times this lever arm, the distance h, times the sine of the angle theta in the minus k hat direction, because it would be rotating as I drew it clockwise around the board. Well, if I look at Newton's second law for rotational motion, if I'm dealing with torques, I need to deal with moments of inertia, and the acceleration alpha, the angular acceleration, is equal to the sum of the torques divided by the rotational inertia of our object. And that would be the rotational inertia calculated around whatever the center of rotation is for our object. So the torque, I said, is minus mass times gravity times the distance h between the center of rotation and the center of mass times the sine of theta divided by the moment of inertia. And if I leave direction aside, just take a look at this piece. The angular acceleration is going to be the second derivative of our angle as a function of time. So the second derivative of our angle with respect to time is going to be some constants times minus the sine of that angle. That is an equation that there isn't a nice, happy, simple, closed form solution for. We really need to use numerical methods and discrete integration practices to actually get a proper solution for this. But as long as we keep a small angle, and in physics we call an angle small if it's less than 10 degrees, we could make the approximation that the sine of the angle is just equal to the angle itself. And the reason why we choose 10 degrees is because the percent difference in radians between the sine of an angle and an angle that would have the radial equivalent of 10 degrees, pi over 18 radians, is right around a 1% difference. So we would be expecting that we'd be introducing a very, very small error making this approximation. Well, that brings us to a regular oscillating equation, where the second derivative of a function is equal to minus the function times some constants. And a solution that fits that equation would be a sine or a cosine. So we're going to use a cosine function. And I'm going to change up my angle to use a capital theta for my function of angle. Looks kind of like a vampire theta. So that's going to have a format that's equal to our maximum angle of displacement times the cosine of an angular frequency omega plus some phase offset, and that angular frequency has to be multiplied by time. Well, you plug that in, take two derivatives here, you get a factor of omega squared that comes out, and then you'd have minus our amplitude times our cosine. You'd have minus our amplitude times our cosine on the other side. So this works as long as the natural frequency of oscillation is equal to the weight of our object, the mass times gravity, times the distance between the center of rotation and the center of mass for our object, divided by the moment of inertia calculated around our center of rotation for that object. And this applies for any physical pendulum. However, let's take a closer look at the simplest of pendula, a particle at the end of a long string of length L. So for that case, the moment of inertia for a particle is just going to be the mass times our radius of rotation squared, which is this distance L squared. So if I take m times g times L divided by m times L squared, the mass cancels out. One of those factors of length from my inertia cancels out, and I get a simple angular frequency for a mass on the end of a string that's equal to the square root of g over L. Thanks for watching.